And we're going to start off with Charles, who's going to tell us about the stellar initial mass function. So please take it away.
Yeah, thanks a lot for inviting me. And I work on several different things that I'm happy to discuss with people, including problems relating to the Hubble tension and some problems relating to machine learning and gamma ray bursts. What I'd like to do is actually to show you some work that we're really excited about, and you're some of the first people to see, other than referees, because 2 of these 4 papers are accepted, but we kind of want to put all 4 of them out together, and the other 2 we're still waiting for the next report. So the idea is a lot of the work that we're doing in galaxy evolution has come out of taking large photometric surveys and then inferring the properties of galaxies from them and using that to build up a picture of how galaxies grow and then eventually quench. So one of the main, let's see if I can make this work. One of the main successes there over the past couple of decades has been what we've called the star forming main sequence. Essentially finding that if we look at the star formation rate of a galaxy, that at any fixed redshift, there's a very tight correlation between that star formation rate and the existing stellar mass. And this is actually maybe a little bit surprising when we think about it theoretically, because if we try to ask, okay, we have a galaxy, what do you need to know to predict the star formation rate? Well, even if we just think about it like a Jeans mass calculation and some balance between gravity and thermodynamics, you would expect that everything that affects the mass availability, gas density, gas temperature, and other gas conditions should be important to this problem. But observationally, we get a much simpler answer that we can predict the star formation rate essentially just from the existing stellar mass and the redshift. So this is telling us that there must be some kind of strong feedback that's basically driving different initial conditions to cause galaxies to grow their stars in the same way. And I'm going to come back to a little bit revised view of this in a few minutes. But I should also point out that everything we're doing here, really when we get a star formation rate or a stellar mass or properties like this, what we're doing is we're taking just the very high mass stars that dominate the luminosity, and we're inferring the rest of either the young stellar population or the entire stellar population from doing that. And so therefore, that's going to depend upon an assumption we're making about the stellar initial mass function, or just the mass distribution of stars at formation. And this is one of the historically difficult problems in galactic astronomy. There have been many different IMFs proposed just from observations of the Milky Way. And unfortunately, I can't tell you that sort of one of these is right. But what I can say is that even thinking about the main sequence, that of say a couple dozen studies that are all finding a star forming main sequence, well, actually these studies are assuming a range of different IMFs. So several of these are in common use today. But in all cases, what we're doing is we're essentially assuming that the IMF, whichever IMF you prefer for Milky Way measurements, really is a universal answer. That because we essentially only see the tip of the iceberg and have to infer the rest of the iceberg, and there's only one iceberg that we can see, we're just going to assume that all icebergs are made of the same type of ice. And we've sort of been forced to make this assumption because we can't come up with observational constraints that allow us to do that. On the other hand, I think there are at least 2 good reasons to think that this probably shouldn't be universal. So the first is that if we change temperature or some other conditions in star-forming regions, this really should change both the initial collapse and then the subsequent fragmentation processes that determine the IMF. And working with Adam Germain, who several of you may know from the Flatiron, we actually tried to figure out how this should work. So we took a Krupa IMF as a model, and then we basically asked for that Krupa IMF, what happens if we start changing the temperature in star-forming regions? And the answer we get is that as the temperature goes up, essentially you get a greater fraction of high mass stars. So you get either a top heavier or bottom lighter IMF.
I'm sorry, that's a statement about a theoretical model that incorporates. Tell us a little bit more about what.
So what we did here is essentially we looked at a Krupa IMF, because a Krupa IMF, you can at least have sort of a semi-analytical way of determining where essentially one of these breakpoints comes from some kind of initial Jeans mass calculation, and the other then comes from a subsequent fragmentation process and looking at how thermal fluctuations build up. And so the idea is we basically ask the same question, But then we asked, well, what happens if you change the temperature and you just perturb it a little bit? How would that perturb these various breakpoints? And so generally, as you might imagine, when you increase temperatures, you need more gravity to do anything. And so basically both of these breakpoints are going to move up in mass. And we're one of a bunch of groups that have looked at this over the past century or so and kind of asked a similar question. All of these are essentially giving you the same sort of answer. That is to say, all of them are telling you qualitatively that as you go up in temperature, you get top heavier or bottom lighter IMFs. For the remainder of this talk, what I'm going to do is I'm going to sort of take the temperature in our model and label it sort of this TIMF. And our hope is that this TIMF really represents a gas temperature directly, but with some of these other either semi-analytical or numerical prescriptions, what we'd find is that our TIMF is an indicator of the gas temperature. It's in all cases normalized so that 20 Kelvin basically is a Milky Way IMF, but that the exact normalization might change a little bit. But the first point is that if we change the temperature in star-forming regions, it should change the answer, right? At a minimum, this means that at very high redshift, we know it's going to change the answer. Because at a redshift of 6.3, the CMB temperature gets 20 Kelvin. So for the highest redshift galaxies we're finding with Hubble, or the ones we're about to find with James Webb, hopefully within the next 6 to 12 months, we know we're going to have to deal with a top heavier or bottom lighter IMF in order to correctly infer the properties of those galaxies. But at the same time, even at lower redshift, although it's difficult to measure gas temperatures in star-forming regions, we do have dust temperature measurements. So there's no guarantee that these are in equilibrium, right? The dust temperature, this is a luminosity averaged dust temperature. So if you have dust at different temperatures, this is kind of going to be more like an average T squared or T to the fourth. So it's going to kind of be biased toward the high temperature end. Whereas if you have molecular clouds at a range of temperatures, the star formation is going to be biased towards the coolest clouds that are easiest to condense. But still, the hint is that if we look at dust temperatures in star-forming regions, typically we find that they're above the temperatures in the Milky Way, and that there's even a redshift dependence and a star formation rate dependence and some more complex behaviors. So what we're doing then is we're taking these large photometric surveys. In our case, we're taking Cosmos because it has 30 bands, and so it gives us the best chance to constrain things. We're taking the same kind of photometric template fitting approach that has been taken in the past, where we take a variety of different templates generated under different conditions. We take these synthetic templates, but now what we're doing is we're going to do the experiment of trying to add one additional parameter to correspond to this family of IMFs and gas temperature and see what that experiment gives us. And exactly what that does depends upon these templates. So these bluer star-forming templates, because they have a larger stellar population, when I change the IMF, these bluer star-forming templates show significantly more variation. And so it's going to be easier to pick out the IMF for a star-forming galaxy potentially than for a quiescent one. This also makes it look like what we really need is the very blue end of the spectrum in order to pick anything out. It turns out to be a little bit more complicated than that, because we start from one of these templates, but then we have to add a bunch of additional parameters in order to actually turn this template into something that matches the photometry. And the one of these that has the largest covariance essentially is extinction here. So that if we change the dust, that's another way of making the spectrum redder or bluer. It's not quite identical. The dust is essentially going to be an exponential change. The IMF is going to be a power law or sum of black body change, something like that. And so in principle, given enough bands and high enough signal to noise, we can tell the difference between them. But we still really need not just the blue end, but kind of the entire spectrum in order to tell the difference between a power law and exponential. And this is what one of these looks like in kind of one of the well-measured cases. We can just look at how the chi-squared changes when we assume different temperatures. And you'll notice that although we get a clear answer here, this is also a relatively shallow dip in chi-squared. And this is
chi-squared, not chi-squared per degree of freedom.
That's chi-squared per degree of freedom, sorry. But it's still relatively...
This is 30 band photometry.
Sorry, no, you're right. This is the raw chi-square. I'm sorry. Yeah, this is the raw chi-square. Sorry, this is the raw chi-square. Yeah. Sorry about that. So the point is that for any one individual object, the uncertainty in temperature is going to be substantial. What we're doing, though, is taking advantage of having a large catalog. There are nearly 2 million objects in Cosmos. Now, because
these are redshift restricted, a subset of those, or how? Or this is the
single
whole
catalog.
no, this is the whole catalog. We're just doing this for the whole catalog.
But what we're looking at here is a single galaxy.
This is one single galaxy in Cosmos, and just looking at how the chi-square changes if we fix different choices of IMF and ask which one fits best, right?
And that's typical of any of them.
This is typical of one of the better measured ones. And so one of the things that we had to do was to kind of ask, well, how well do you have to measure things? And for the typical one of the 2 million objects in Cosmos, this is mock data kind of characteristic of it. We're just not really able to recover the IMF from synthetic photometry. So this really only works for about the 5% of objects with the highest signal to noise in Cosmos, which means we're really measuring this for something like 130,000 of the objects in Cosmos, generally on the high mass and bright end, because that's where we get good signal to noise. But for those, we actually do get a well-constrained answer. And so we can start to look at what the properties are.
And there it's limited by, so you're firmly limited by signal to noise, which would imply that, you know, in a magical universe where you could tune your data to fit your needs, that had you had broader bandwidth in your photometry bands, you would have been a happier person.
I think either broader bandwidth or deeper, some combination of the two.
So but you're not seeing any real benefit of having higher resolution in that photometry.
No, I don't think the resolution helped here because you're not trying to pick out a specific line. You're more trying to pick out what you really want is the difference in shape.
Yeah.
That's a good point. Yeah. So basically, it's just signal to noise plus as much spectral coverage as we can, and that's really what we're seeing. Okay. So what do we find? Okay. Well, the first thing is we find that most galaxies are fit with a higher temperature than the Milky Way. And part of this makes sense. This is what we expected from dust temperatures. But there's also a surprising feature here that it seems like most galaxies at any fixed redshift actually kind of cluster around one characteristic gas temperature or IMF. And at first we thought this was quite surprising. But on the other hand, if we think back to the star forming main sequence, what it's telling us is there has to be some kind of strong feedback that's driving galaxies to all grow their stars in the same way. Presumably what this is telling us is, well, conditions in gas and star forming molecular clouds are part of that feedback. And therefore, if galaxies are all growing their stars in the same way, we should expect that they have similar conditions. And so I think that might be the way to interpret this. Now, when we do change these temperatures, is that an issue?
It's fine.
Okay.
University thinks we're shadow weather panic.
Okay.
It's all good.
Okay. Okay, no problem. All right. So if we then think about kind of the implications of these temperatures, right? One is that essentially all of the other properties that we infer are going to change. In some cases, it's because they're highly covariant. So for example, the amount of extinction that we fit is going to change, kind of in the opposite way that the IMF does. But maybe more importantly for our purposes, the stellar mass and star formation rate are also going to change, because if we have a top heavier or bottom lighter IMF, then this means that we're going to get the same luminosity from a much less total stellar mass, either for the entire galaxy or just the young population. So if we then go back and kind of look at the star forming main sequence, not all that much has changed in terms of the overall distribution. We still get this tight correlation between star formation rate and stellar mass at every redshift. The locations of both have moved a little bit, but we kind of still get the same broad physics. Maybe the more interesting feature though, so if we compare these first 4 or 5 panels, because they overlap in redshift with the dust temperatures, what we see is actually very much the same sort of thing. And I've tried to color these two in the same way so that you can compare the colors here and here. So we see really the same features. We see in both cases, we typically have these temperatures above 20 Kelvin. We see in both cases that as you go toward high redshift, the temperature is going up a little bit. We also see that if you fix the redshift and fix the mass, that as we go toward high star formation rate, the gas temperature is going up. And what this seems to imply is that maybe the temperatures in star forming regions, that the part of making this feedback mechanism work is that the temperatures are dominated in some way by the young stellar population, either directly from massive stars, maybe from their deaths via supernova, or the cosmic rays that come out of that. Maybe it's X-ray binaries or something about fueling a central supermassive black hole. But basically that in some way, the young stellar population is the dominant source of temperature. And this maybe even helps to build a feedback mechanism, right? That if we imagine that the temperature places a limit on the star formation rate via Jeans mass-like calculation, but then that star formation rate also is the dominant contribution to temperature, then we can get an equilibrium solution. So this is kind of the picture we get for star-forming galaxies. There is one significant difference, though, between the dust and gas temperatures, which is that in the gas temperatures on the very high mass end, we get these lower temperatures, which are not seen in the dust case.
Sorry, I'm not sure where I did.
So just at the very high mass tail,
At the right.
yeah, just at the very high mass tail, there's this dip in temperature, which is not something that we see in the dust.
But that's only at low C. That doesn't exist at high C.
Well, the highest mass objects at any redshift, essentially what's happening is the highest mass objects at any redshift just start to be a little bit cooler than the rest of the star forming population. And sorry,
How much should I care about when square?
so I've tried to kind of give you the density over here to give you an idea, because a plot like this often emphasizes the outliers a little bit, right? So I tried to give you the density here for comparison. The point is the bulk of the distribution looks like what we expected from dust temperatures. And that's a really good sign, because this is an entirely different way of measuring temperature. So it's a really good sign that we get the same answer. But at the same time, the question is, well, what's happening on the very high mass end, right? So I think a hint there is if we just look at quiescent galaxies, we get different behavior.
We have to define in practice now.
This is sort of UVJ or UVJ and no MIPS detection or something like that.
Okay.
So if we look at quiescent galaxies, there we don't see these elevated temperatures. We see something much more like the Milky Way.
We still see.
Yeah. Yeah, there seems to be like a transition period, right? Like you have a
Yeah. So I think I took the slide out where I overlapped them. The other one kind of comes here. Is the issue? No, I don't have the slide where I overlap them. Okay, so the idea is that quiescent temperatures are lower, right? And so if we're really optimistic, maybe this actually gives us a hint as to what's happening. Because if we select galaxies on something like UVJ, right? So the blue galaxies are star forming and the red ones are quiescent. Well, if we turn off star formation in a galaxy, it may take half a gigayear for it to change from blue to red. But on the other hand, if we measure the IMF from the young stellar population, that should be conditions that are more recent. And so maybe if we're really fortunate, what's actually happening here is the galaxies that are blue but have cool IMF temperatures are ones that are in the process of quenching and just haven't changed color yet. And maybe this is even a way of selecting quenching galaxies rather than quenched galaxies. The other thing that this would do is actually potentially solve kind of a puzzle, where for everything else that we've learned about galaxy evolution, what we're finding is that galaxies of a given mass and given redshift kind of are all behaving the same way when they grow, right? And similarly, that there's even some kind of hierarchy, you know, a bunch of results that we often kind of collectively term downsizing, where generally the more massive galaxies go through these different stages of their evolution first. But if we take, say, the cosmos mass functions, and we just compare the distribution of star forming and quiescent galaxies, and we look at what fraction of galaxies are quiescent at different redshifts, well, then it suddenly looks quite different, right? What we see is that the first galaxies to become quiescent, or these purpler ones, are actually in the middle of the mass distribution. And that actually at most redshifts, we see that, some of the galaxies are quenched and some of them haven't. It really looks like a different sort of process than the rest of star formation. It almost looks like an external process that's being imposed, because everything else about star formation you would expect to be hierarchical, and you'd expect all of the galaxies in a common mass to be doing the same thing. But now, if we think about the fits that we're getting where we allow the IMF to vary, we get a much simpler answer, because the quiescent galaxies, really not much has changed. You have a more Milky Way-like IMF, and so you have similar inferred parameters. But for the star-forming galaxies, what we find is we have this top-heavier IMF. And so all of these masses get pushed to the left. And the more we go toward high redshift and the temperatures go up, the further they're getting pushed to the left. And so if we do the same comparison with our fits, we actually get a much simpler answer. What we simply find is that at any redshift, the most massive galaxies have quenched, the least massive galaxies are still star forming. There's some transition mass in the middle. And then as we go toward lower redshift, sort of toward red here, I should have drawn this opposite, shouldn't I? As we push to the left, right, we just find that we're kind of progressively pushing toward low mass, so we even get this same downsizing idea. This bottom picture, I think, is exactly the one we would have predicted if we didn't have these observational results.
So that's the part here is the quenching fraction.
That's the quenching fraction, just using the new stellar masses that we're getting, having allowed the IMF to vary.
And new star formation rates.
And new star formation rates, but I guess this is really just a mass function. So once you've classified it as red or blue, then you just need the stellar masses to do this. Okay, so there's one last surprise I want to show you that we're really still trying to understand, and I'd be eager to hear some opinions on what might be going on. So this is really preliminary to the point that we haven't even cleaned up this plot yet. So a bunch of these hexes only have one individual object in it. What I'm showing you here is essentially the distribution at some narrow redshift range of the specific star formation rate or star formation rate per unit mass, kind of for all the galaxies in the sample, as compared with the temperature that we're getting. And you should really focus, kind of on these contours, because that's where most of the distribution is, right? So actually, almost all of the objects lie in that upper left-hand corner. This is really where the star forming main sequence is, right? But the interesting thing is that we do have these two tails to the distribution. And one of them, I think, is easy to understand, that we have a very low star formation rate, right? We have the high mass end. So essentially, these are the quiescent galaxies. But the thing that's new that we hadn't anticipated is what's happening kind of on this horizontal branch here, right? And we do know that this horizontal branch is happening on the very low mass end. So it's kind of tempting to think about it as some kind of early stage of star formation. And if we look at how this changes with redshift, we get the same picture, right? That toward high redshift, the quiescent galaxies, of course, are gone because they haven't had time to quench yet, but we're also seeing more and more galaxies in this horizontal tail.
Sorry, very stupid question. Why is so horizontal, like it seems to have a scale built in it, right?
Yes. That's a good question. I'm not sure. One possibility is that there's inherently a limit on the specific star formation rate you can sustain. For example, maybe there's an Eddington-like limit where if you just have too high of a star formation rate for the gas density, it stops new things from collapsing. It's not quite clear, though. So I think the point, though, is that we're sort of tempted to label this as either this is the typical star formation, but this is some kind of early star formation. Yeah.
This object's not in sequence, right? I mean, the specific star formation rate is the same as as the dense form, more or less.
Similar, yeah.
But they're quite different.
But they're getting very different temperatures. And one of the things I'd really like to know is if we can get some ALMA observations or something from a handful of these and see whether we're seeing the same thing either in CO or C+, something. Unfortunately, it's a small set of galaxies, and because it's on the low mass end, we need to put in a follow-up proposal to actually do this. But that would be one of the key questions.
They may be lower redshift analogs. These objects.
Yeah, this is a redshift 0.8 already, kind of what I'm showing you. So I'll give you the best idea that we've got, but like I said, I'm looking for some good ideas here. The idea we're thinking about is that if the star forming main sequence is really driven by this feedback between temperature and star formation rate, right? So for quenching, what happens is you turn off the feedback in one direction. The star formation rate is no longer the dominant contribution to temperature. What if you go in the other direction? What if you have such a high gas density that an increase in star formation rate does kick the temperature up, but doesn't come back and limit the star formation rate because you're always above some kind of Jeans mass calculation due to the high density? And in particular, what if we imagine that basically, if you take a galaxy, right? If you imagine that this galaxy formed from something maybe like an NFW profile initially, right? You start with a very high baryon density in the center. The idea would be that that first phase really is something that can only happen at very high densities. And so what it's doing is it's kind of describing, I don't want to say bulge because the morphology is maybe a different question, but it's sort of describing central star formation. And maybe this would even help explain why protogalaxies do appear to be so compact, that only the centers can form stars. And this would predict that if you're able to get good measurements of the full gas density, you would see that they extend further out than the starlight, right? And then the idea would be that the star forming main sequence is really more like disk star formation. So that's the best idea we have, but I'm definitely interested in some other ideas here. Kind of to sum up then, so I think the point is basically that what we've really done is to do this experiment of asking what happens if we take these big photometric surveys and we allow the IMF to vary and see if we can fit it. And first off, we do get the answer that there is some different IMF. We cannot just use a Milky Way IMF. We are actually getting evidence that other IMFs fit better. The IMFs that we fit, broadly speaking, are really in keeping with what we expect if gas and dust are in equilibrium. And that's a good sign that we're measuring something meaningful as part of this fit. It doesn't really change the star forming main sequence so much, but there is kind of this difference between star forming and quiescent galaxies. And so one of the things it might do is then change our idea for kind of the order that things turn off and really suggest that quenching is not some external process imposed upon a galaxy, but just the natural consequence of having been on the star forming main sequence for long enough. So some kind of gas depletion mechanism, for example. And then finally, there's even kind of this hint that maybe there's something a little bit more complicated going on very early in a galaxy's evolution, and that maybe galaxies grow their stars in a little bit different way than they do in most of their lifetime on the main sequence. So let me thank you again for inviting me and take some questions.
Thank you very much. Let's do, in the interest of time, like one question, if that's fine.
Oh, my question is a very long one, so I'm gonna put shout out to anyway. So I'll talk to my other anyway.
That sounds like a great plan. Yes, we have like a short question, maybe.
How about stupid?
Yeah.
Okay.
This is the question most interesting, though.
Is it understood on your bottom right plot what the left branch is that sort of independent of mass
these couple?
and very low temperature? Yeah.
So, those?
Yeah.
I think as I was mentioning, often these are populated by sort of one object.
Ah, okay.
So I think those are mostly just
Gotcha.
things where
that are
it's
there.
not great. I think I mentioned
And that's
this
why the
is-
contour doesn't capture that. It's just not.
Yeah, that's right, because there's basically nothing there,
Got
but the way we plotted it, if there's one object out of the 40,000 or something on that plot, then it gets a hex. And I think by the time we publish it, we'll probably clean that up a bit.
Great, thank you all very much. Thank you very much, Charles, again
Thank
for
you.
doing this talk. And I think let's now
Sorry.
probably move on to Andrea, and let's see how that's gonna go.
Yeah, let's see.
So do you want me to leave this
I think so.
open, but you connect through your computer? Is that the?
You have to try it.
So do you, no, you don't see that? Oh, it is not, okay.
Can you maybe stop sharing your screen?
Oh, I'm sorry. I thought I had.
I'm already sharing apparently, so I don't know.
Have I not shared my screen?
But-
It's
At
it's
some
on
point-
the Zoom.
At some point,
Aha, but you need
yeah,
that.
at some point, Andrea's laptop was online.
That's the problem. Yeah, because it's on the Zoom.
Right, typically if I'm just a normal participant, I can typically
Yeah,
share,
exactly,
right?
exactly.
So I don't know what was happening, but typically, you know, I'm sharing now, so I don't know what was going on there.
I completely agree. I thought it should.
Yeah, it should like, exactly, if he's talking to share,
Yeah,
it should have like be there,
exactly.
but for some reason.
But there was a
The
moment
other
where it
thing we
was
can do-
showing.
Giovanni, non ti stiamo sentendo, stai parlando.
Here, if you give me that back, I
Let me
can.
try again because
Let me share let me change what's up on the screen and see if that works instead. Now I think this will work. Maybe, let's see. No.
So you
Um,
can now pull up the Zoom. Yeah,
Aha.
fantastic.
okay, good. So Giovanni, can you see now?
Does that work?
Okay, so, okay, yes, okay,
Great.
Giovanni said, can you hear me well? If I speak like this, because the microphone is a little bit, yeah, I don't know where is the microphone.
I have my.
Oh, chat something. Yes.
What Giovanni is saying? Yes, okay, he said yes, okay, good.
Great.
Okay, so let me start so that I will not steal time for lunch. So first of all, I want to apologize to the people from the IAS because they are probably sick of me. I talked to IAS 2 times, like 2 weeks ago, and now a third time. But okay, let's see how it goes. And this talk will be much more astrophysical in some sense, but with a lot of hints also for cosmology. And for example, Misha Ivanov, that is in the audience, actually helped us a lot. I'm a particle physicist, like for, you know, just for the one of you that don't know me, but I like a lot astrophysics and cosmology. So the talk start, I want to talk about what is called the excess in the arcade measurement. Okay, I don't know if you all know this experiment. Arcade is a balloon that is measuring radio waves, okay, in the frequency band between 3 and 90 gigahertz. Okay, he put out some result in 2009. Okay, he has, I think, like 6, 7 like frequency beams, and he's measuring the antenna temperature in a very actually small patch of the sky. Okay, so what I will plot here is just the antenna temperature as a function of frequency. Okay, now if Arcade was just measuring some black body temperature like the one we expect from CMB, right, we should just have some constant temperature here, right, around 2.7 or whatever is the CMB temperature, right? While Arcade is measuring something like this. So there is some excess of Arcade, okay, over the frequency beams that is measuring, okay? That of course is much below Cobi and Figas, right? Much lower frequencies, okay? And then what is also nice that Arcade, this measurement is also consistent with other measurements from other actually radio frequency experiment at lower frequency, running also at earlier time, that were all measuring an excess much above the one that you would just expect from CMB. Okay, and this excess is all these experiments are different experiments. I think that we have like 4 or 5 of them. They all measure the same power law in the temperature. Okay, now like this in more particle physics friendly, although probably you don't need it, but let me write it. The antenna temperature basically as a function of the energy or frequency can be written in this way. So basically it's just the number of photons that you get in the frequency beams of your experiment, okay? And what they measure and the fit that you can do is something that looks like this. You have the CMB temperature, okay? Plus you have a power law that looks like this, 2 pi gigahertz to the alpha, okay? It takes some time to appear. With this TR is 1.19 Kelvin, okay? And this alpha is something like minus 2.6. Okay, so you see that at large frequencies, basically we recover the CMB temperature, but at small frequency, there is a huge excess. Okay, this 2.6 in the antenna temperature also means that basically we are injecting photons, okay, proportionally to omega to the minus 1.6. Okay, so roughly omega to the minus 3 alpha. Okay, and this is interesting actually because astrophysicists and astronomers, they don't understand where this excess is coming from. Okay, this is there for more than a decade and still they don't understand. What I'm plotting here is actually the excess after subtracting the galactic contribution. Okay, but of course, astrophysicists are smart people, so what they tried to see at the beginning was, okay, maybe we didn't do a good job. Can actually this excess be a galactic one? Okay, and the answer seems to be no. Okay, the main reason to me, at least when I read the literature, seems to be actually X-ray observation. Okay, let me tell you why, just the basic physics. Okay, when you see a power law like this in astrophysics, of course, we all know that we immediately think about synchrotron radiation, right? There will be some charged particle with some spectrum, right, in some magnetic field, accelerated and emitting this radiation. Okay, but now, just back on the envelope, the magnetic field, imagine that you are injecting some energy with some rate due to this synchrotron radiation. Okay, this will be proportional basically to, okay, the Thomson cross-section, just Thomson cross-section, the energy scale, the energy density in the magnetic field, so B squared, okay? And then some factor like the gamma factor of the charged particle that is just telling us how energetic are the particles that are accelerated, okay? Now, in the Milky Way, we know that more or less for just, Faraday rotation measurement, the magnetic field should be around the microgauss, right? So this means that in order to match the observation of this plot here that I was showing, for this given magnetic field, the particle should be very energetic. Okay, and if this particle around there, that actually would inverse Compton scattering the CMB, okay, and it will produce actually a diffuse kind of X-ray background above the one that we measured. Okay, so at the moment, actually, I think that whole agree that this cannot be a galactic contribution. We also have actually other reason to believe so. Our spiral galaxy will be very spatial, like having some very extended halo that no other spiral galaxies show. Okay, so we astrophysicists really think that actually this excess is extragalactic. Okay, so this is an important piece of information. So this is extragalactic. The answer is yes, seems to be. But, okay, it's not that clear actually what this can be. Because if astrophysicists try actually to take dim sources, let's say there is a huge population of, for example, the galaxies that we've been talking to in the previous talk, like star-forming galaxies, galaxies that are emitting, but we don't see them because they are very low luminosity. This population should be very huge, okay? There should be a very large number of sources, okay? And actually, these galaxies should be actually also very peculiar, because we know that in many galaxies, we observe a kind of radio far infrared correlation in emission, right? Just because far infrared is associated also with stars, right? And the radio with that kind of gas and synchrotron radiation. So we typically observe this correlation. So if this radio excess was due to galaxy, for example, a low redshift, okay, then we should also see a much bigger infrared background. Okay, so basically it's just to say that astrophysicists and astronomers, they all think that actually only, a very small fraction of the excess can be due to a galaxy, a number of even single sources that are too dim to be detected right now. Okay, so at the moment, as far as I understand, the best solution that astrophysicists proposed is actually the presence of intermediate massive black hole with a mass. So these are not supermassive ones. So this is also important. It's have not been seen. Okay, this should be black hole with some mass around, let's say, 10 to the 4, 10 to the 6 solar masses. Okay, forming around the redshift of 20. Okay, and the physical mechanism is actually very simple. What people think is that you have star 3, pop 3 stars that basically they will explode like supernova-like, with this just scaled up supernovae. So this energetic particle will be accelerated during this process, and then it will generate some synchrotron radiation that we then see. Okay, but what I want to highlight even this solution is a kind of like, it's an hypothesis, right? Because we don't know when and if this black hole form in that way. Maybe they form in completely different way with merging of smaller black holes, right? So this at the moment is the best solution, okay? But it's also just, you know, an hypothesis that is not very well tested at the moment, okay? And also I want to mention another thing. It's really also important that whatever source you have, it should not come from small redshift. Okay, because there is an extra ingredient that is puzzling in this excess, that this excess is actually very smooth. Okay, if you look, for example, there is a paper by Older from 2012 with VLA measurement, and if you look at basically fluctuation of the temperature at the arc minute scale, this should be around like 10 to the minus 2. Okay, so basically this puts very strong, it's a kind of very homogeneous like background seems to be, okay? And this puts very strong kind of constraint on the physical mechanism that you want to have, right? Let's imagine that I want to have some, let's say that my source that is producing this stuff, I call it F as a function of redshift, okay? And then let's say that I imagine that this source, because they are galaxies, so it's dark matter, is somehow correlated with the power spectrum. Okay, then I can work in Fourier space and I can calculate, for example, just in a very simple sketch, the CL, okay, of this stuff. Then it will be just an integral over the covooling volume. I will just sketch it of whatever is producing this excess, okay, and then some power spectrum, okay, as some multiple L in the, you know, like as some redshift. Okay, you can work in the Limber approximation. This is not really important, okay? But then what I want to say is just that if this source is coming from, let's say, a redshift that is smaller than 5, okay, then basically you get a very large CL, and then you are against observation. Okay, so this is also one reason why typical astrophysical of like, you know, explanation kind of fail, many of them. So they have to, you know, to rescue this intermediate massive black hole at very large redshift. Okay, so of course, like, you know, the universe is filled with dark matter. Okay, then when this excess came out, actually people started immediately to propose dark matter models to explain this excess. Okay, and so for example, in 2011, my collaborators, actually Marco Regis, Nicolau Formengo et al. from Turin, they proposed one of the first model of dark matter to try to explain this excess. Okay, and this model is just a very simple one in which you have dark matter scattering. So let's say that I call this particle chi and chi bar. These are the dark matter, typical WIMP. Okay, then this will scatter, and then this will produce like let's say electron and positron, for example, or whatever other charged particle, depending on the mass and whatever. Okay, then this will be accelerated in the B field. Okay, and then this will generate actually synchrotron radiation, for example. But actually, this model doesn't work really well. The fit is not good enough, actually, in my opinion. If you look at the papers, it was a very nice idea, but they actually screw up also with the CL, because they have, you know, it's a scattering process, so everything will scale with the density square. So it's very correlated with structures. It's coming actually with structure on small scales. So basically, this kind of explanation is kind of ruled out. Okay. And so now in the last, let's say, 10 minutes or less, I will try to, you know, like to make some, you know, point of why we think that our model that we are working with people actually from NYU and actually also Princeton, Ongwan Liu, and also MIT, Siddharth Mishra Sharma. We have another type of model. It's always dark matter based. So we always have a dark matter candidate, but we have an extra ingredient that I want to explain to you, and also for which is very important that you cosmologists give us the, you know, the PDF of baryons, and you will understand why. Okay, so the model here is kind of simple. Let's call now dark matter A, okay? Just because I have in mind the new dark matter models. Maybe you heard about this. This is typically you talk about axioms, okay? This is the one that I have in mind. If you heard about this new proposed particle, it was proposed actually by Bilchak, although this is not the QCD axiom. Then this axiom, this dark matter, will decay, okay? And decay in what we call dark photons, okay? Don't get scared by the name. The dark photon is just something very similar to our photons, but lives, let's say, in the dark sector. There are very good motivation to think that, you know, we can have these particles out there, okay? But then actually this particle, what happens is that it mixes with the photon, okay? This actually if you have some background of particle physics, I can write down the Lagrangian, and will just be what we call a kinetic mixing term, in which this is the field strength of our U1 of electromagnetism, and this instead is a dark sector. Okay, but this is not really important. What is really important is that we have a dark matter that decays into this dark photon, and then this dark photon basically oscillates to photon. Okay, this oscillation you can think about really similar to neutrinos, right? In neutrinos, you have oscillations between different flavors. Okay, in this case, you have oscillations between this dark photon and the photon. Okay, so basically in this model, we just need three ingredients. First of all, dark matter. Okay, but this we have to have it in the universe, so it's just free. Then we have a dark photon. Okay, and then we have a mixing between dark photon that I call dp and our ordinary photon. Okay, so this is all we need. Okay, and then if we have a transition like this, I will show you a plot, a very nice plot in which we basically have a perfect fit with the data. Okay, what actually one need to have this conversion? I say that this is very similar to neutrinos, right? If you know a bit about neutrinos, the fact, when we saw also neutrino oscillation, this is the way in which, and actually, I'm happy to be here at Princeton and DIS because John Bacall was one of the pioneers of that, right? We understood the neutrino have a mass also because of this kind of oscillations, right? Now, the point is that the dark photon, okay, can have a bare mass. Let's call it Ma prime. Okay, it's just in the Lagrangian, we can give it a mass and it's there from the very beginning. But then we know that in principle, photons, they don't have a mass, right? However, when photons, and probably you know better than me, and now here in Princeton we have amazing plasma physics, when you are in a plasma, actually photons do acquire a mass. Okay, it's not, of course, it's not a gravitational mass, right? It's just a gap, let's say, in the dispersion relation, but they do acquire a mass. And this is called the plasma frequency. Okay, let me call it m gamma. Okay, and this is just basically related to the density of the electron that you have in your medium in which your electromagnetic excitation is propagating. Okay, so basically, if your photons is propagating in a medium with electrons, it will have a mass. It will pick up a mass that is typically called also, if you take any condensed matter book, it's just called the plasma frequency or the plasma mass. Okay, so why cosmology is important? Because in order to have we can draw a plot like this in which I plot the plasma mass m gamma of z as a function of redshift. Okay, now a plot will look like this. Okay, so here, what you have here, this small thing that you have here is recombination. Okay, when the electron fraction drops, okay, so the plasma mass starts to drop. Otherwise, it's just redshifting before that, just because the density of electron, right, will redshift 1 plus z to the cube. Okay, before that, this region here that looks very spiky and complicated, I guess that you already guessed that is reionization. Okay, in which the free electron fraction also changed quite fast. And just to give you an idea of what the scale is, this value here is around 10 to the minus 9, let's say, electron volt, while the value here is around 10 to the minus 14 electron volt. Okay, these are the scales that you have in mind. If you consider just an homogeneous universe, okay, with the homogeneous density of electron that we can guess from our universe. Okay, and then what happens physically is that if now you have a dark photon mass that, let's say, lies here. Let's say that my dark photon mass, this Ma prime here, right, the one that I have it here. Okay, let's say that it's 10 to the minus 11 electron volt. Just an idea. Okay, then at this point in time, okay, that is probably close of redshift, let's say 100 or so. Okay, at this point you see that the two lines intersect. So this is actually a point in which the plasma mass of the photon is basically the same of the bare photon mass of the dark photon. Okay, so that is the point in which actually, if you start with the photon, okay, you can convert to a dark photon or vice versa. Okay, so this is really what is similar to neutrinos and what's happening, in the path, for example, between neutrino and the sun and us, for example, in some sense. Okay. Now, what is really important, that we take care of cosmology is the fact that, of course, this is a very simple picture, right? I'm saying that basically the electron density is just homogeneous. We know that at small redshift is not true, right? So what will happen is actually is that the electron density, okay, at some redshift z, will be the one, the bare one, or like the homogeneous average one, plus some fluctuation, plus the fraction of, the fluctuation in the electron fraction. So what actually will happen is that here, the plasma mass will not be like, this kind of smooth line. We'll have some oscillation with some scale that is basically the scale of the fluctuation in the electron density. Okay, so now we have to have a way in which we want to treat these oscillations. Okay, and so we basically have to have the statistics. Okay, the power spectrum in some sense. Actually, in our calculation is enough to have the power spectrum of this object here. Okay, of this fluctuation here, and how the statistics of this fluctuation. Now, actually, let me go and in the last 3 minutes, let's say I go to normal Zoom presentation. Can you see? Can you see my screen? See what's going on here? Okay, see. Okay, good. So basically, let me go fast on this. Here, here is just a scale picture of what I was drawing in the. Can you get rid of the chat there? This is just a picture of what I was drawing before. Like the homogeneous, this is just the plasma mass that I was drawing on the iPad, right? The dashed line is what you expect in the homogeneous universe. And this, instead, all these oscillations are done if you just simulate a box with a Gaussian power spectrum and just see how the plasma mass looks like. Okay, so the oscillations in the matter field will reflect in the oscillations in your plasma mass. Okay, and then I don't have time to discuss it. We develop basically an analytical formulas to calculate the conversion probability between the photon and the dark photon. Okay, and this looks like this. Okay. Of this function, it doesn't really matter if you understand all the point. What it really matters is this function here, this f. This f is the PDF for the plasma mass. Okay, this is basically saying how probable it is for a photon traveling through the universe to encounter some mass, okay, of the plasma. Okay, and this correlates on how probable it is for my photon to encounter an underdensity or an overdensity in the baryon field, for example. Okay, so what you really have to give me, and then I can do the computation and calculate this PDF, is actually the baryon density fluctuation, okay, and the PDF for the baryon density fluctuation. The one that we know that, we actually can relay that also to the electron one, and can we do our computation, okay? And this actually, I can come back with this. It may look weird to you that I was talking about electron density, and now I talk about baryon fluctuation, right? They are two different objects, okay? But to give actually an analytical prescription, you can actually treat density fluctuation in electron density and fluctuation in baryon density the same. And this will actually just matter, will be very different during reionization, for example. But apart from that, the fluctuation will be very similar, okay? And so, for example, at large Z, you can use some Gaussian, for example, PDF for the baryons. We know that it works pretty well. So you give me the variance, so you give me the power spectrum basically, and then I can do the computation. At low Z, when things go actually more nonlinear, okay, we adopt different prescriptions, okay? So for example, we use a log normal PDF that is typically, what also a lot of people see. Misha told me that there is no reason to believe that, theoretically this should be the case, but it actually seems to work. Then we also adopt like an analytical prescription that actually Misha was nice enough to guide me in using it. Okay, this is just based on some nonlinear spherical collapse for dark matter, and then we adapt it to baryons, putting in some extra information about the gene scale, for example. And then in order also to test our underdensity, we also took some simulation of cosmic voids. Then we kind of extract a PDF from that, and then we also tested how our log normal was doing good in sampling low densities, right? And actually, I'm putting a lot of things under the carpet because in order to draw the log normal, okay, you have to know also, the variance, for example. okay? And when you go to low redshift, for example, you cannot just use class, right? Because things are becoming very nonlinear. So what we actually do is actually we take simulation like Illustris, the Eagle simulation. We take the power spectrum that they provide, and then we compute the correlations, and then we compute the PDF, okay? And then we use all this. We do what I was telling you. So basically, our model is like the dark matter decay is very simple. It produces this dark photon, and then the dark photon oscillate with this formalism that I was telling you. So at the end of the day, we started with dark matter, and we are injecting photons, okay, that we want to detect. And this is actually what we get. So this is basically the first plot that I draw as a first slide, okay? It is the excess, the red point here are the arcade excess, and all these other red points here are the other frequency, okay? The blue line is actually our fit with our model. So we get a very good fit. I don't have actually the reduced chi-square here, but the fit is really good. So we think that we can explain the excess with this very simple model. And actually, I also have a parameter space that probably you don't care much about this, but this is just the parameter space of my MCMC, like in sampling the dark matter parameter space. And so I think that we have a very nice, explanation of the excess. Of course, we need, for example, to treat better at some point, and any help will be, welcome to treat better, for example, reionization and the fluctuation of electrons in that period. And but I think that this is again a very nice interplay. This is what I do typically, to have this interplay between particle physics, astrophysics, and cosmology. We have a lot of unexplained excess that we probably can explain if we collaborate together. And Princeton is a great place for this. So thanks a lot for hosting me, and then I'm happy to take questions now, and also if you just want to drop me a line by email. So thank you.
Yeah, are there any questions for Andrea? Let's do one.
Yeah, it's like.
Well, I can also ask a question this time. So you mentioned early on that the dark photons are well motivated by other things. I've never heard about it before. What are those things that motivate having dark photons?
So for example, one of the things that motivates is that apparently it can be very easily dark matter. Okay, because for example, the point is that if you couple dark photon during the inflation just with gravity, so you just have a dark photon with mass, okay, you can do the computation, and then from gravity, like there is a paper by Peter Graham, for example, showing that without any non-minimal coupling to gravity, okay, just putting there, solve the equation of motion, it will be very easy to produce the correct relative abundance. Okay, so this is one simple explanation. Another thing is that it's a very minimal extension of the standard model. So we are just saying there is an extra U1, okay, that is there. You also have motivation from string theory, but I'm not a string theorist. So probably there are other people in the department that are more expert than me, okay, but also is motivated in that case. And the axion also is the same. It's also motivated, for example, in theory by string theory. There is this paper also, if you think about fuzzy dark matter and out, there is this review by Witten, Lam Hui, in which they also have some connection with string theory and why these particles are motivated. So these are the theory motivation. But then is also that typically when we have unexplained excess, these are typically the first particles that are used to do that because they are simple and they connect very well with the standard model, right? It's just, yes.
I didn't mean to interrupt.
Sure. Go ahead.
So what would this do with the dark energy equation of state then if you add?
That's a good point. You can actually have model of axion, an axion-like particle that kind of, this kind of dark energy, for example. You remember the first paper by Mark Kamionkonski, in which have this Hurley dark energy that actually didn't work because of sigma 8 problem, but they have something like that. That was actually an axion-like inspired model because it was just a kind of cosine potential, just not a linear order, a higher order, but it is kind of like axion inspired. Okay, and that actually was, but in a completely different mass range than what I'm talking about here. Here, the axion is much heavier. It's like 10 to the minus 3, 10 to the minus 4 electron volt, and completely different also scale of the decay constant. Yes. But in this case, this dark matter, just tau relics, so it's not behaving like dark energy. With this parameter, never, basically. Okay, so it's always like it's a good cold dark matter candidate.
I think let's just, let's just prioritize the IAS for
yes.
the last question, and then everyone else can ask questions.
So I have a question about the plot with the extragalactic background. Like you had two explanations. Like the extragalactic background, you said you do match the intensity, but you don't match the fluctuations, like angular fluctuations. So do you have?
No, that's a very good point. I didn't show it here. The point is that. Yeah, thanks for the question, Jay. One of the good things of this model is also that we don't go above, because that is just an upper bound from the fluctuation, because it's just a measurement, right? So one of the good things of our model is that actually, I don't have a slide here, but that when we compute the 2-point correlation function and the CL, they're much below, they're typically a factor of few below the measurement. And the physical reason is the following. Here, the decay of dark matter is happening at large redshift, like around redshift of 10 or above, and then you convert later on, okay, but still in a spread mass like redshift range. So basically in this model, you don't have also the problem of the other, models of WIMP, for example, in which the excess was really coming from low Z, and so you screwed up the 2-point correlation function. That's an amazing question, but we are also fine on that. I think that we are probably the only model with dark matter fine with that.
Okay, and so you have, like, I missed that. Like you said, these are not the entire dark matter, these dark photons.
No. It is the entire dark matter. Of course, you can also play with the fraction, and if you play, for example, with the lifetime, we still have space, so you can even do a fit with, let's say, just 10% of dark matter. But even if it is dark matter, because of the parameters, okay, the decay is happening very early. So the point, for example, also with decaying at low Z, is that when you compute just the CL, right, and then you do the computation with the power spectrum, if the decay is happening at low Z, basically dark matter will have structure imprinted in it, right, in the decay, let's say. So also the power will have them, right? But while if you can plot actually the decay, as a function of Z, okay, in our model with our mass and our coupling, and the decay is basically happening much before, just because then you have to convert in dark photon after that. Okay, so basically it's completely mass range and coupling range as compared to WIMP scenario, and so the decay is happening early on. This is the reason. But it's the entirety of dark matter. You can have full dark matter in this axiom.